Hey guys, it's Miss Johnson and I'm here to bring you our second part of chapter 12.3 notes. Today we're going to talk about estimating the parameters and also finding a confidence interval when we are doing inference for slope. So when the conditions are met and we can do inference about a regression model that looks like in the form of a linear equation, the first step is to estimate the unknown parameters. So if we calculate the sample regression line, meaning y hat equals a plus bx, just a regular old linear equation, the residuals estimate how much y varies about the population regression line. So you can use these statistics to estimate the parameters. That's what they're getting at here. So all of these three are statistics coming from the regression line from the sample, and they can be used to estimate the parameters that are in the population regression model. So when the conditions are met, the sampling distribution of the slope B is approximately, and the sampling distribution of the slope B is approximately normal, with mean of the sampling distribution equaling the population slope, and the standard deviation looks like this. So we estimate the variability of the sampling distribution of B with the standard error of the slope. So again, this is your population standard deviation of the sampling distribution. We can use that, or I should say, instead of using that, we can use the standard error of the slope. So the standard error is interpreted as how far the sample slope typically varies from the population slope if we repeat the data production process many, many times. So let's talk about a question here. It says, earlier, Mr. Barrett's class used computer software to perform the least squares regression analysis of their helicopter data. So we're going back to that helicopter example where they dropped them from 5 different drop heights. Recall that the data came from dropping 70 paper helicopters from various heights and measuring the flight times in seconds. Some output from the regression analysis is shown here. We checked the conditions for performing inference earlier. So yesterday we did, or in the last lesson, we did the conditions. We talked about LINER. We had that acronym LINER, and we went through and checked all of those conditions and they were all fine. So now we're going to go through these 4 parts right here. So the first part says, what is the estimate for alpha? Interpret this value. So alpha is that y-intercept, the y-intercept of the true population regression line. So part A is asking us, what is the estimate for alpha, and to interpret the values. So we're going to take a look at this computer output, and really this whole example is just practicing reading computer outputs like this one. So you're going to see computer outputs like this on your AP exam, and we have to kind of be able to pick out what data we need from these types of computer outputs. So for alpha, remember that alpha is the y-intercept of the regression line. So if we are looking at the y-intercept of the regression line, we want to look at the constant, and it's under this coefficient column right here. So the constant is negative 0.03761, and in this case, we're talking about seconds here. So I would say that A is equal to negative 0.03716 or 761 seconds, or I just name that as a value. And then I would say, to interpret it, if a helicopter is dropped from 0 centimeters, it will take negative 0.03761 seconds to land on average. Now, of course, we know that there's no such thing as negative time. Okay, we know that that's the case, but we're talking about an estimation of the regression from a sampling distribution. So the sampling distribution, when we repeat the sample over and over and over again, gave us a y-intercept that was just a teeny tiny little bit below 0, because we know in our heads, if we drop a helicopter from 0 centimeters, it should take 0 seconds for it to hit the ground. Theoretically, we're basically there, Because this comes from a sampling distribution and not the true population parameter, you know, this is estimating the parameters, we are at that slightly underneath, slightly negative value. Okay, so that's just an illustration for you of how sampling variability comes into play when you're looking at things like this. So now let's look at the next one. So let's look at beta. Now we're going to look at the slope. So what is the estimate for beta, or in other words, the slope of the regression line, and then let's interpret that value. So for the slope of the regression line, now we're looking at the drop height part, because drop height is your x. So this is the coefficient that goes in front of x, which is then what would be your slope. Okay, so it's beta times x, coefficient from the drop height, which is x, there's your slope. So beta is equal to, or b I should say, is equal to 0.0057244. And what that means, if we interpret that, is for each additional 1 centimeter in drop height, the average flight time increases by 0.0057244 second. Okay, fraction of a second. So when you are interpreting a slope, you have to remember that you're going to address an increase of 1 unit of x. So whatever your units of x are, that's what's increasing, and then address that changes the y. Okay, next one, what's the estimate for the standard deviation? So now we're going to get into standard deviation. Okay, so for a standard deviation in a population, or in a sampling distribution, that's our S value right here. So then what does that mean? So S equals 0.168181. And if we interpret that, it says the actual flight times typically vary. Remember, standard deviation is talking about typical variance. Typically vary by about 0.168181 second from the times predicted with the LSRL. Remember that acronym? LSRL. Oh, and then we have to name x using x equaling the drop height. So what you're getting at here is the fact that actual times typically vary from predicted times, okay? Actual times typically vary from the predicted times by that amount. Okay, and then the last thing, we're gonna look at that standard error. So in part D, given the standard error of the slope, so now the value in the table that we're looking at, again, slope comes from drop height, but we're looking at the standard error coefficient, so we're actually looking at this value this time. So remember that it's beta times your x is drop height, and beta is your slope. So here's our standard error of the sampling distribution of slope. So what does that mean? So SE of the standard error of the sampling distribution of B is equal to 0.0002018. Now, what this gets at is this is your standard error coming from the sampling distribution. So if we repeat the random assignment many times, the slope of the sample regression line would typically vary by about 0.0002018 from the slope of the true regression line. For predicting flight time and from drop height. Oops, flight time, predicting flight time from drop height. All right, woo, there's that. So that's kind of a tricky one to understand. What the standard error comes from is the sampling distribution. So if you can recognize that it comes from a sampling distribution, whenever you think sampling distribution, you think repeat the process many, many times. Repeat the random assignment many, many times and graph it out, okay? So that's kind of where standard error comes from. All right, so then let's just give our definition here. This is we're going to get into constructing a confidence interval for these things. So remember that a confidence interval comes from whatever our statistic is. So that's going to be the B value because we're doing inference for slope. Then you take that plus or minus, you find the critical value, and you find the standard deviation of the statistic. Now, these critical values come from T star, not Z star, because this is from the sampling distribution, not from the true population. So we have to use T star, which means that we have to do a degree of freedom. And for linear regression, our degree of freedom is n-2, which is a little bit different. So we're looking at n-2 for degrees of freedom. Then that standard error comes from that standard error equation that we saw. So again, these are all equations that you'll have in your sheet, in your formula packet, like for the AP exam. It's just you being able to pick out which equation you're using. All right, so here's just a caution for you. The values of T given in the computer regression output are not the critical values for the confidence interval. So you saw a T value in that computer output. That's not your T star value. That's a different T value. All right, so now we're going to get into a question here. We're going to actually calculate a confidence interval. It says, everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used Ford F-150 Super Crew 4x4 if we know how many miles it has on the odometer? A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed for sale on autotrader.com. The number of miles driven and the price in dollars were recorded for each of the trucks. Here are the data. This is good to know. Whenever you have data, that should suggest to you L1 and L2. Just saying. Okay, so then on the next slide, here's what we're given. Remember I said you'll be given all of these graphs if you have to do this on the AP exam. So here's what you've got. You've got a scatter plot of the data, basic scatter plot of the data. It's very clearly linear. You can see the regression line that they drew through the middle. Then you are given the residuals. So the residuals of the data. So remember, this is how far away they are from the regression line. So basically, what is their variance? What's their variance from the regression line? Okay. You want to see random scatter. Random scatter looks good to me. Then you're given a histogram of the residuals. Okay, so here's a histogram of the residuals. This is kind of an interesting looking histogram, but remember they talked about how don't get too nitpicky about it. It's okay to use a histogram that doesn't look completely perfect. And then you're also given that computer output data where you've got the constant, you've got the X, so this would be your slope, that's your Y-intercept. Then you get the standard error stuff for the sampling standard deviation. You also get your standard deviation of just the line. All right, here we go. So here's some computer output from the least squares regression analysis of these data. Construct a 90% confidence interval for the slope of the population regression line. All right, we start with state. We got state plan do conclude. Here we go. 90%. We're doing a confidence interval here. So 90% CI. And yes, you can abbreviate that for parameter. Remember, you're doing confidence interval for parameter, which in this case would be beta, which is the slope of the population regression line. Which relating y equaling price to x equaling miles driven. And then you got to talk about the car, which it's like the longest car name ever. For used Ford. Here we go. F-150 Super Crew 4x4s. Listed for sale. Oops. For sale on autotrader.com. All right, holy buckets. Here we go. So that's our statement. Now we're going to... Okay, so when we get into plan here, this is where we've got to list what we're finding. We're finding a t-interval for slope. Again, it's t because it's a sampling distribution. This is not population. And it's an interval because we're doing a confidence interval, and then slope is the variable we're looking at. Now, conditions. So your conditions, don't forget about liner. There's a lot of conditions for inference for slope, but that's okay. We can do it. So L, we know that the scatter plot is linear. The scatter plot shows a linear pattern, and the residual plot shows no curved pattern. Great, check. Okay, I, independent. As we assume that 16, we have to state, because this is a sample drawn, so we have to state the 10% condition here. So we're going to assume that 16 is less than 10% of all used F-150s Super Crew 4x4s. Oh, I forgot to say Ford. Ford F-150s Super Crew 4x4s. Okay, N. Normal. So there's no strong skewness or outliers in the histogram of the residuals. That's true. There's no strong skew in the histogram of the residuals. Now, it's not the most pretty histogram that we've seen, but again, we don't want to get too caught up in that. It's okay that it's not the most beautiful histogram. It's all right. As long as it's not completely skewed or totally, there's a huge outlier somewhere or whatever, then it's okay. Now let's talk about the equal standard deviation, because this is kind of a funny one. So in the equal standard deviation, we're looking at the scatter of the points on the residual plot. So look at the residual plot. As long as your scatter shows about the same in the positive and in the negative, and they're about the same distance away, there aren't any that are really aggressively far away for all the x values, then it's okay. So the scatter of points around resid equaling 0 appears to be about the same for all x values. Okay, and then the last one, random. Random's usually pretty easy to address. So this is a random sample of 16 used Ford F-150 Super Crew 4x4s. Okay, here we go. So there's our plan, which it's kind of crazy because it takes us a little while, but you got to name the test and then you got to list all the conditions, which inference for slope, there's a lot of them. Okay, moving on. Here's our do. We're going to get into the do here. So for do, now we're going to actually talk about all the things we need to talk about. So our degrees of freedom is going to equal 16 minus 2, which is 14. That's that n minus 2 right there. Okay, let's talk about T star for a second. So this is going to be a blast from the past for you. So T star comes from, if you want a 90% confidence interval, this is 90%, right? So if I think about a normal curve, I want 90% to be my interval. That means I have 5% in each tail, right? So there's a couple of ways that you can do this. You can go to the table in your, in the back of your book. There's a T star table, T table. Or in your calculator, you can go to second distribution. And then distribution. And you want to do inverse T because you have the proportion underneath the curve, but you need the value that marks that proportion. So when you go to inverse T, you're looking at an area of 0.05 and a degree of freedom of 14. So 0.05, degree of freedom 14, and then I paste that, and so you get, remember this is where you would get a negative output, so negative 1.761. We transform that into our positive, 1.761. And that just comes from the fact that it's the T value on both parts. So they gave you this one. That's what the negative 1.61 value is, but it's also the same as that one. And we want to use a positive because we're constructing a confidence interval. So we don't want to change the sign of our values. So 1.761 is our T star, 14 is our degree of freedom. You have the slope that was given to you, the distribution slope from that computer output, plus or minus the T star of 1.761 times the standard error value, which was also given to you from the computer output. So 0.03096. So these two values right here came from the miles driven row, which is the X variable in that computer output. So the first one was that negative 1.16292. That's the sampling distribution slope. And then the other one is the standard error of that sampling distribution. Okay, here we go. Then we actually calculate it. When you actually calculate it, you end up with negative 0.16292 plus or minus 0.05452, and then your confidence interval actually ends up being negative 0.21744 to negative 0.10840. Okay, there's your confidence interval. Now let's talk about what this actually means. So let's write a conclusion here. In our conclude statement, okay, we want to address the confidence level. So we are 90% confident that the interval, and then list the interval, negative 0.2174 to negative 0.1084 captures or contains or whatever, contains the slope of the important word here, population, because we're always doing confidence intervals for populations, regression line, relating, and then list your variables. Y equaling price, and X equaling miles driven. Now talk about what it is you're looking at. For Ford F-150 Super Crew 4x4s. They even keep going and say listed for sale on Auto Trader. Ooh. All right. So there's our conclude statement. There's your confidence interval for slope. Now, like any other good statistical analysis, we can use our calculator to help us. So here we go. In your calculator, remember how I said you had your data? Pop that X data into your L1, pop that Y data into your L2, and then you've got ln reg t interval as one of your options. If you go to stat and over to test, the linear regression t interval is one of your test options. For me, it's like way down at the bottom. Ln reg t interval is option G, very, very low. And then you're going to be asked, where's your data for L1? Where's your data for L2? What's your confidence level? So you always have to give the confidence level. And then this is the computer output you get. You get the confidence interval right there. So that's your CI. You get the slope, you get the degrees of freedom, you get your S, you get an A value. So the y-intercept for this was 38,254. Makes sense because you're talking about money here, price of a new truck, basically. And then you get the R squared and R, which is that correlation, if you remember. Correlation. Okay. What you don't get here is you don't get the T-star value. But again, that's something that you can look up with inverse T on your own. Okay, if you do inverse T, just remember that you're looking at two-tailed, so 90% on the inside, it would mean that you've got 0.05 in each tail. So if you needed to get the T-star value, then you can do that one in inverse T, and that was in second, I can write a 2 here, second distribution is where you get inverse T. So use your calculator to help you is my point there. All right, here's your AP exam tip. It says when you see a list of data values on an exam question, wait a moment before typing data into your calculator. Read the question through first. Often information is provided that makes it unnecessary for you to enter all the data in, and that can save you time. So while in this case, it may have almost been just as fast for you to type the data into your L1 and L2 and then do the confidence interval from your test menu, you also could have done what we did without needing to type it all in. You know, we did the confidence interval without typing in the data. So it is possible to not need to put all that data in. 16 entries for each X and Y is not too bad. I mean, if you're looking at 30 entries, maybe that's going to take you a little longer. You have more of a chance of making a mistake, entering something in wrong. That's kind of what they're getting at there. All right, so this is the second part of inference for slope. So thanks for tuning in, and I will catch you for the last part of section 12.3.